Jai Hind to all of you. My name is Dr. Ritish Kumar, and I am going to give the lecture on measurement in the microwave at microwave frequency, various parameters such as voltage standing wave ratio, also known as VSWR, impedance measurement, and dielectric constant measurement. So these topic has been mentioned in the syllabus of unit number 3 and 4. So before starting the topic, what is the utilization of measurement? So if I say about the VSWR, it stands for voltage standing wave ratio. That means it specifies the reflection which has been observed by due to the mismatching happening in the loads and input impedance as well. While for the case of impedance measurement, we need to find the characteristic impedance and the impedance of the waveguide by using this measurement technique. And apart from that, we will move further the dielectric measurement that will be useful for to get the knowledge of the medium. Now let's begin with the topic, the measurement of VSWR. As I said, the VSWR stands for voltage standing wave ratio. So VSWR has some range which has some boundary value through which, if the value below that value, that is the 10, that is the value of 10, if the value is less than 10, when we will consider this one is a low VSWR, while if it is greater than 10, when we will consider it into the high VSWR. So there are different techniques to measure the low VSWR and the high VSWR. So first we will start with low VSWR technique. So here I have mentioned this component. This is nothing but a slotted waveguide section in the measurement setup. So if I say what is the microwave test setup to have this slotted waveguide section, so I have mentioned this measurement setup block diagram for the to set the microwave test when setup. So this is a microwave source where in the lab we are using the reflex klystron, then pad slotted line section, that is nothing but the slotted waveguide section, and through which we have connected a crystal detector, and through the crystal detector we detect the power, and we will able to see the power through some measuring device such as VSWR meter, multimeter, and CRO as well. So this is the setup block diagram to measure the different kind of parameters such as VSWR, reflections as well. So this is a slotted waveguide section. You can able to see here that is this is a scale made over this waveguide, and if you and this is a knob, and you can you will be able to move in the forward direction and backward direction as well. So as we know, what is the VSWR? VSWR is the ratio of VSWR is the ratio of V max by V min. So we need to identify what should be the value of maximum voltage and what should be the value of minimum voltage at the output side. Right. So in the for the case of low VSWR, we need to adjust the attenuator in such a way to have the maximum voltage while in the next step we need to move this node in such a way so that we can have the minimum voltage at the VS at the CRO device, at the CRO output device. And when we are able to have the maximum voltage and minimum voltage through this experiment, so we can get the ratio of these two, and we are able to get the VSWR from these two values. How it will be, how you will get it? So actually this device is connected over here. If you move this snow either in a forward direction or backward direction, once you will get once you get some maximum voltage, then if you move further in the forward direction, right, then you will get the minimum voltage and maximum voltage respectively. So you have to find this value V maximum and V minimum. Actually this curve is drawn from distance versus voltage. Why? Because this is a distance, and if you move this over this waveguide, you will get the some voltage over the CRO device, over the CRO output device. So you have to you need to get the value of the ratio of V maximum and V minimum. So you will get the value of VSWR. So this is the procedure of getting the low VSWR by doing this experiment or by doing this microwave test fan setup, right? So I think this measurement of low VSWR is clear to all of you. So if you are able to get the VSWR, here I am representing this VSWR as YS. So if somebody asks what should be the value of reflection coefficient, then you need to know the formula. You need to know the formula of or we can say you need to know the relationship between the VSWR and reflection coefficient. So reflection coefficient rho is equal to S minus 1 upon S plus 1. Here you can also write VSWR minus 1 upon VSWR plus 1. If you get the value of VSWR, then you will be able to get the value of reflection coefficient. And one thing you need to remember, that the range of VSWR, right, the range of VSWR is in between 1 to infinity, right? In ideal case, the value of VSWR always be equal to 1, right? So this is about the VSWR. Now what technique we will use to measure the high VSWR, right? This is the technique of high VSWR. So the method that we will use here, the double minima method, right? Similarly, as we all are aware in the last slide, that what is the slotted waveguide section. So there is a knob, you can able to move in the forward direction and backward direction as well. So this is why we are calling this double minima method. If you move the knob in a particular direction, here I am moving the knob of the, here I am moving this knob in the forward direction, in this direction only. So what will happen, once you get the maximum value at particular location, and then if you move in the forward direction again, then you will get the minima value at certain point, and again you will get the maximum point at some location. This kind of periodic nature we will be getting after moving the knob in the forward direction, right? So why we are calling this double minima method, so we need to consider two minimum point here, right? Two minimum point, this. So as we know, this is the two consecutive minima distance always be equal to lambda z by 2. Why? Because lambda z by 2 here, lambda is the guided wavelength, because the wave is propagating through a guided media, right? So this is a lambda z by 2. So so you can look at here, the distance between two minima is lambda z by 2. If I consider it, that is, if I consider this one is d1 and d2, you can get this d1 value through this by, oh, you can have this d1 value by using this scale, and d2 again by using this scale. So both value are you already know from this scale, and this value lambda, this the difference between these two value is equal to lambda g by 2, right? So from this method, by using two consecutive minima, as this distance is d1 d2, so lambda z by 2 is equal to d2 minus d1, so lambda z equal to 2 times of d2 minus d1. So from this you can get the guided wavelength, right? Now now as here we are considering, now we need to calculate the value of high VSWR here. So here we are considering the point or 2 point where the Vx is equal to root 2 times of V minimum. So here from this reference point, if you there are 2 points in the forward direction, this point is, you will get by moving the knob in the forward direction with respect to this reference point, and in the backward direction again you will get this point with respect to this reference point, right? So these 2 points you need to get by using, again by using a slotted waveguide section, and you will have this these two distance value from the scale that is made over the slotted waveguide section. So there is an empirical formula to get this high VSWR. This is an empirical formula of VSWR, right? Lambda g you already know by you with the help of the experiment of, or d1 d2 you all d1 d2 also you will get from the slotted waveguide section here, and after putting the value of all the parameters in this equation, in this empirical equation, then you will get the VSWR value, right? So again we can say, if I want to know the reflection coefficient, then you will then you need to know the relation between Vs reflection coefficient and VSWR. That is the relation of reflection coefficient and VSWR. So this is the technique of measurement of VSWR by using double minima method. Why? Because we are considering two minima to calculate the guided wavelength, that is, this is minima number 1 and this is minima number 2. Here you are considering two minima, that's why we call this method is double minima method, right? I hope this measurement of VSWR is clear to all of you. Now the second parameter, that is impedance measurement using a magic tee, right? The device of magic tee, I think that is clear to all of you in the second unit. That is a combination of E and H plane tee. Also we can say this is a hybrid tee, right? So hybrid tee is a 4-port device. Here we have mentioned the 4-port, port 1, port 2, port 3 and port 4. Here port 4 is the E plane and port 3 is the H plane, is in the H plane, right? So to measure the impedance of unknown impedance, so this is a setup that we need to create. That is, at port number 1, we need to connect a standard variable known impedance, and the impedance that you want to know, that is unknown impedance, need to connect at the port number 2, and at port number 3, a microwave source is connected at port number 3, while at port number 4 we need to connect a detector. So this is a setup that we need to create to measure the impedance of unknown device or unknown impedance, right? So what should be the procedure? Well, when you give the input, that is incident wave, that has the voltage is alpha 3, right? So if I say in terms of power, that is delivered from this source, and this power is equally divided in these two port number 1 and port number 2. In terms of voltage, that should be 1 by root 2 of this incident voltage. That's why we have taken 1 by root 2 here, 1 by root 2 alpha 3, 1 by root 2 alpha 3. This is a in other terms we can say this is power division, equal power division. Now this is a incident wave, right, and this is a reflection through the mismatching of the device. Actually by default this is a waveguide, and this waveguide has a characteristic impedance Z0 that is differ from this standard variable impedance. Due to the mismatching of the impedance, the reflection would occur in this waveguide. Similarly at port number 2 here, right? So that's why we have reflected voltage here, and this reflection, so that's in this voltage we have mentioned the rho 1 here, that is a reflection coefficient. So reflection coefficient we have considered here, and this is the reflected voltage. So this is again the voltage that is received at the null detector. Why we are considering the negative sign? Why? Because at port number 1 and port number 2 we are considering the input as the same phase. When the two inputs at the Z1 and at port number 1 and port number 2 in the same phase, then we at port number 4, and that is E plane, we will have a difference of these two. That's why, yeah, these two input are in the opposite phase. That's why this sign, this is negative sign, is negative sign. Negative sign is negative shows the polar 180 degree phase shift between these two values, right? So why we are calling this is null detector? So the resultant value that we will get at port number 2 is the difference of these two value, right? If these difference of these two value is equal to 0, then we will have a null detector. What should be the condition? So if you solve this equation, you will get rho 1 is equal to rho 2. That means the reflection coefficient or reflection from port number 1 and port number 2 is equal to when both reflection coefficient are equal, then you will get a null detector at port number 4, right? And another condition is if you in terms of impedance, if I consider this Z1 and Z0, Z1 minus Z0 divided Z1 plus Z0 is equal to Z2 minus Z0 upon Z2 plus Z0. If you solve it, then you will get Z1 is equal to Z2. So if these two impedance is if these two value are approximately equal, then you will not get anything at the port number 4. So So you need to adjust the value of this impedance in such a way so that you will get the null detector. So you will get at the port number 4 is equal to 0, that is null. So so at null detector we already know that this value will always be equal to this value, right? So in this case Z1 is equal to Z2, right? I think how we can able to measure the impedance using this magic T, I think this one is clear to all of you. Now the measurement of dielectric constant, how we can able to measure this dielectric constant. Dielectric constant, so if I say what should be the property of the media always be defined by using the three properties sigma, mu and epsilon, right? Sigma is the conductivity, mu is the permeability and epsilon is the permittivity, right? So here we need to focus over the permittivity, right? So permeability, mu is the related to the magnetic force and conductivity is related to the dielectric charge, right? The dielectric constant epsilon is the measure of efficiency of transfer of electric charge. At we are already aware about this line or statement. Dielectric constant is also referred to permittivity of the media. So this is the relation of relative permittivity, that is epsilon is equal to epsilon naught and epsilon r, where epsilon r is equal to epsilon prime minus j epsilon double prime, right? Where the tan delta is equal to epsilon double prime upon epsilon prime and is known as loss tangent, which is equal to the ratio of power dissipated to the power stored per cycle. So the setup that we need to consider here is a slotted cavity perturbation method. Here we are considering the cavity resonator. Here we have connected VNA, that is vector network analyzer. VNA stands for vector network analyzer. So by using this analyzer you can able to see scattering parameters, and resonating frequency. So without here we have considered the sample of the material that need to know materials, right? So here a simple material we have taken in a simple tube, a very narrow tube, and once I insert this tube into the through this slot. Here this slot is known as non-radiating open slot, right? But first you need to take the reading without using this sample, then you will get some resonating frequency over the VNA, that is S21 reflection, S21 parameter. You need to take the value from the VNA, that is and this frequency is known as resonating frequency of the cavity resonator. And after filling you need to take again the value of S21. Here you can see this is a sample 1 and this resonating frequency shift from this to this, right? So you need to take the difference of this resonating frequency without considering the sample and with sample. After putting this value in these two equation you will be able to get the value of cavity. You will be able to get the value of dielectric constant of this material, right? So VC and BS is volumes of empty and sampled filled cavity, and QC and QS is the quality factor of unperturbed and perturbed cavity. So I think this one is clear to all of you about the measurement of dielectric constant. I think these three topic, that is VSWR, impedance measurement, and the dielectric constant, all are clear to all of you. Jai Hind to all of you.